There are snow flurries outside in Atlanta, and I can't think of a better time to solve triangles. To solve a triangle, what we want to do is take the given information about angle measurements and side lengths and use trigonometry and things like the Pythagorean theorem to find the other unknown angle measurements and unknown side lengths. In the first example, we know two sides and we're given a right angle at angle C, but we don't know the other two angles and we don't know side B. In the second example over here, we're given one side length and one acute angle, and also a right angle, and we need to find the other two sides. So the techniques that we're going to use are going to be slightly different. In the first triangle, it's easiest to first find side B, because from the Pythagorean theorem I know that 9 squared has to equal 5 squared plus B squared. And so we get 81 minus 25 equals B squared, or in other words, B equals the square root of 56. And because 56 has a perfect square factor, we can think of this as the square root of 4 times 14, which, 4 being a perfect square, we can take the square root of that part of it, of that factor, and we get 2 square roots of 14. So that gives us the length of B. B equals 2 square roots of 14. To find the angles, well, for angle A, the two side lengths that are given, and it makes the most sense to try to work with the side lengths that are given because they give us more exact measurements. Although 2 square roots of 14 is also an exact expression, if you converted that into a decimal, it would become less accurate and could cause problems. But taking, for angle A, we can take 5 and 9, and we know that sine of angle A equals 5 over 9. Because relative to angle A, 5 is the opposite side. So then, with a graphing calculator, we can take the inverse sine, which is the yellow command above the sine key. The inverse sine function, it accepts a ratio, it takes a ratio as an input and gives us an angle as an output. So I want to double check before I jump to conclusions here. I want to double check and see that my mode is set to degree mode, and it is. So the answer that comes out is in terms of degrees. If it was in radian mode, the answer would be in terms of radians. And so we can conclude that angle A, using the inverse sine function, I know that angle A equals 33.75 degrees, rounding to 2 decimal places. And because these two angles have to be complementary, I know the other angle is going to be 90 minus 33.75 degrees, or 56.25. In the second example, we're given one of the angle measurements, and so right away the easiest thing to find is the fact that over here this would have to be 55 degrees. Again, because the two acute angles in a right triangle have to be complementary. And then to figure out D and F, well, let's think about this. We could either take 35 or 55 degrees and create trigonometric ratios. If I take sine, oh no, that's not going to work, sorry. If I take tangent, let me take tangent of 55 degrees. That will give me the ratio opposite, which is the unknown side D, over 10. And so to figure out what the value of D should be, I can multiply 10 on both sides so that D equals 10 times the tangent of 55 degrees. And then with a calculator we can figure out what that value should be. We get 14.28. And at this point we could use the Pythagorean theorem like we did in the first example to figure out what angle F is, but to be more precise, it's best to stick with the side length that we know, that we haven't rounded at all, that we haven't approximated. Because 14.28 is an approximate answer for what the actual value of d would be. So let's think about a trigonometric ratio we could use with 10. So we could either take sine of 35 to get f into the picture, or we could take cosine of 55. And let's take sine of 35. Let's say we know that sine of 35 degrees is, well, relative to 35 degrees, 10 is the opposite side over f, which is the hypotenuse. And now to solve for f, I want to multiply both sides by that denominator. So if I multiply f to both sides, I get f times sine of 35 degrees equals 10. So f equals 10 divided by the sine of 35 degrees. So if I take 10 and then divide by sine of 35 degrees, we get 17.43 as the value for f. And there we have it. We've solved the right triangle. These two examples illustrate some important differences between right triangles that you may want to solve. In the first one we had two sides were given. In the second one we had one of the acute angle measures and one of the sides. And so the strategies that we employed were different. And what I'd like you to think about as a question, to extend your understanding of this specific question toward a more general understanding, try to summarize the general strategies that were used to solve these triangles. And what I mean by that is to write out in words the situation, the steps that you might follow, the strategies you might employ if you're given two side lengths of a right triangle and asked to find the angles and the other side, and if you're given one angle and one side. And in this second case, there were a couple important differences between finding D and finding F that you might want to think about. So think about that. Take a few minutes. I very much encourage you to, and try to stretch your understanding to a more general one. Thanks for watching.